All right, in this video, we're going to talk about the Poisson distribution. So this is one of my favorites. I remember when I learned about this in my stats and management science class, and I like this. These are exciting. These are, I think, fun to solve. I don't know if you share my enthusiasm, but hopefully some of it wears off on you. So again, remember we're working with discrete probability distributions. We already learned about the binomial. Now we're learning about the Poisson. So the difference between these two is the Poisson is used when determining the number of occurrences over a specified interval, usually over time, but sometimes over space. So think about, for example, the number, right, the number of occurrences, so the number of customers entering a store between 8 a.m. and 9 a.m., right, and it's over a specified interval. Another example would be the number of cars arriving at a car wash in a 1 hour time frame or interval from when they're open. So whenever you see something about the number of something and then some type of interval, 8 a.m. to 9 a.m. or 1 hour over 5 minutes, something like that, you know you're working with the Poisson. So the Poisson we can look at the properties of it. So the probability of an occurrence is the same for any two intervals of equal length. And then the occurrence or non-occurrence in any interval is independent of the occurrence or non-occurrence in any other interval. So some similar properties to the binomial. You know, we're looking at, you know, independence, and then similar probabilities for any two intervals of equal length. So we have that there. So anytime you're looking at when you see the rate of something happening, you see an interval, you see the number of something, you kind of know you're working with the Poisson distribution. So remember, what's the difference between the Poisson and the binomial? Remember, they're both discrete probability distributions. They fall under that umbrella. Discrete, remember, you're just working with two outcomes. So, excuse me, so you're going to have like the heads, the tails, the purchase, the no purchase. With the Poisson, you still have discrete outcomes, but there's not just two of them. Typically, there's no upper limit. So, for example, the number of customers entering a store, I mean, there really is no upper limit. You could have 5 people enter, 10, 20, 100. But typically what happens is as X becomes large enough, basically the probability of that near zero, basically it becomes negligible. So what's the probability that 2 people or 3 people or 4 people enter the store? That's typically probably higher compared to maybe 100 if you have kind of like a small store. So that's just kind of the overview of it. The Poisson, distribution, this is a probability function. I'm not going to go through to show you where this comes from like I did with the the binomial distribution. Instead, take this for what it is. I'm going to spend more time showing you an example because with the examples and the problems, I think they're a little bit more involved and a little bit more complicated than the binomial. I also want to point out that the mean, right, the expected value of occurrences in an interval is known as mu, but sometimes it's also referred to as lambda. When I learned about stats, I learned it as lambda. And sometimes in other stats books, other references, you'll see that as well. Sometimes I get caught up and I refer to as lambda. So if you hear or see me referring to lambda, probably talking about the mean or the expected value of a Poisson distribution. The last thing I want to point out is that the mean is typically given to you, but the mean and the variance of a Poisson distribution are actually the same, just so you know that. Okay, so let's do an example. So here's the example. Phone calls arrive at the rate of 48 per hour at the reservation desk at an airport. So again, we kind of already know that we're working with the Poisson, right? Phone calls arrive, right? And phone calls are discrete. You can even get 1, 2, 3 phone calls, right? It's not as though someone can make 1.2 phone calls. So how many phone calls are coming in, right? Those are discrete numbers. It's a discrete variable. And then we see rate. Anytime you see rate, you know you're working with the Poisson. So we got 48 per hour. So what we need to compute is the probability of receiving 3 calls in a 5-minute interval of time. Again, interval of time, you know you're working with the Poisson. Okay, so how do we solve this? Okay, so here's the problem written on the right, just so we can reference it, and here's the solution on the left. So typically whenever you have problems, it's good to write down the information that you have. And this is true for any type of, especially mathematical problem that you're trying to solve. Write down the information that you know, that you don't know, what you're trying to solve for, and then work from there. So what do we know? phone calls arrive at the rate of, so this is the mean, right? It's the rate, it's what's known, right? So mu is 48 calls per 1 hour, right? So this is the average, this is what we're given. But what do we want to solve? We want the probability of receiving 3 calls in a 5-minute interval. So we want to know, right, 3 calls in a 5-minute interval. So we're interested in solving for this 5-minute interval. This is what we want to know. So if you'll notice, the mean and this 3, what we're interested in calculating, the probability, are not on the same scale, right? 48 calls per hour versus 3 calls per 5 minutes. We need to always make sure that we're on the same scale. Otherwise, if you just start plugging in your mu is 48 and you're looking at 3 calls, so x is 3, you're not going to get the right solution, or the right solution, because you have different intervals, right? So remember to make sure you're always working in the same interval. This is a 1-hour interval, this is a 5-minute interval, not the same. So we're interested in solving this right here. We're interested in solving for a 5-minute interval. So we need to get this hour into a 5-minute interval. So we have to convert this to a 5-minute interval. How do we do that? Let's convert mu to be on the same scale as x right here. So let's start with what we know. We know that the mu right now, the mean, the expected value, is 48 calls per 1 hour. But we want it in a 5-minute interval. So we want to basically change or convert hours to minutes. So basically what we can do is we can multiply this value right here, 48 calls per 1 hour, by this. Right? Anytime you multiply something by itself, you're not changing anything really. So 1 hour is equal to 60 minutes. So 1 hour is equal to 60 minutes. So what happens is this is just multiplying by 1, right? 1 hour divided by 60 minutes, that's 1, right? Because there's 60 minutes in 1 hour. So this is really all we're doing is we're multiplying it by itself. So we're not really changing this number, right? We're just putting it on a different scale. So typically when you want to convert, right, when you multiply, right, what's in the denominator of one and the numerator in another, they cancel out. So technically this hour, this 1 hour here, and this 1 hour here, right, they're the same, they cancel out, right? It's like multiplying 48 calls by, or if you just had 48 and you multiplied it by 1 divided by 48, right, the 48s would just cancel out. So it's similar, right? The 1 hour and the 1 hour cancel out. So really, we're just gonna multiply 48 calls by the 68 minutes. So they're both divisible by 12. So 12 goes into 48 4 times. So we have 4 calls. Calls is the what we're going to have in the numerator, right, because the hours cancel out, so all that's left is calls. And then 60 is divisible by 12. It goes into it 5 times, right? So we have 5. And what's the units on the denominator? Remember, the hours canceled out here, so all we have left here is minutes. So our solution now is 4 calls per 5 minute. Well, per 5 minutes, sorry, I left the F's off there. That's great, because what are we interested in? 5 minutes. We want that interval. Well, guess what? Now we have it. We have our mu on this interval of 5 minutes. So we basically converted this 48 calls per hour into calls per 5 minutes. We've put it on the same scale as this. So basically now we're both on the same scale. We're interested in, for a 5-minute interval, right, what's the average? 4 calls. What do we want to know? Well, the probability of 3 calls in that 5-minute interval. So now that's what we have. We have mu is 4. X is 3, what we're interested in solving for. And now we can just plug it into our equation that we have before, right? This equation that we have from the last slide, the Poisson probability function. There it is right there in the center. So now we have these values. The probability of X occurrences, we're interested in 3 for a given interval. It's a 5-minute interval. And then we have our new mu, the expected value or mean of occurrences in that same interval. Right, we have those values now. So now we can just plug and solve. So, right, mu raised to the x, right, mu is 4, x is 3, times by e raised to the mu, right, is negative 4, and then divided by x factorial, so that's 3 factorial, solve, and you get 0.1954. So basically, what is the probability of receiving 3 calls in a 5-minute interval? It's almost 20%. So that is the solution right there. We can use Excel. We can use the Poisson distribution function, just like for the binomial distribution, we were able to use that function to solve. So let's go to Excel and see how to do this. right? So equals Poisson.dist. And then you have three arguments, x, the mean, and cumulative. So x, right, if we go back to our slide, what was it? It's 3. And then we have the mean. That highlights what's the mean. What's mu is 4. And then remember for this one, just trust me for right now, it's false. I'll talk about true and false when we talk about continuous distributions. Right, 0.1953, right, 0.1953, right, just with rounding, that would round up to 0.1954, right, and that's how we get that. So the Poisson distribution, right, in Excel, really easy, but the problem with using this is you can't just plug in values. You have to make sure you're on the same scale here, right? So if you were just to plug in, oh, x is 3, mean, the mu, oh, it's 48, plug in those, you wouldn't get the right solution because they're not in the same interval, right? Interval, we're interested in a 5-minute interval, but mu is given in terms of hours. So always make sure you're on the same scale before you plug your numbers into your equation or into Excel. So let's do another example. Let's do B just to make sure that this is clear. So now we have the same rate. So we found that before. We already converted it to 4 calls per 5 minutes. Let's just leave it there for right now. Now we want to know the probability of receiving 10 calls in 15 minutes. So now our interval is changed. So now we have to, convert this mu to be on the 15-minute scale. So the good news is they're both in minutes. They're just in a different number of minutes. So going back to basic math, right here we have our mu, 4 calls per minute, but we want to convert it to be on the scale of 15 minutes. So I think hopefully you remember how to solve for this. Oops, sorry about that. What did I do? Basically what you can do, right, is just solve for z, right? We already have what we know here, but we want to convert this to see, okay, well, if there's 4 calls per 5 minutes, how many calls are there per 15 minutes? So you can set these two equal, right, because technically the ratios should be equal. It's just the values that are going to change. So we set 2 fractions equal to each other, right, 2 ratios, and then we can cross multiply, right, multiply 15 minutes by 4 calls, right, to get 4 by 15, and then cross multiply 5 minutes by z to get 5z, and then we can solve for z, right? 4 times by 15 is 60, right, equals 5z. Solve for z, divide by 5, 60 divided by 5 is 12. So now we have, right, just plugging in z, we have 12 calls per 15 minutes, right? So this is our rate. This is mu or lambda. It's on the same scale as this per 15 minutes, So now we have x is 10, mu is 12. Let's just plug those numbers in, right? 12, 10, negative 12, 10. Solve 0.1048. Similarly, if you wanted to plug those into Excel, Poisson distribution, right, x is 10, right? X up here is 10. Mu, the mean, is 12, right? We solved for that. We got a new one over here. We got 12. And then false, right? And we solve it 0.1048, the same as that. So that's a Poisson distribution. Like I said, look for rates, look for intervals. You know you're working with a Poisson. Make sure that you get on the same scale before you plug into Excel or into the formula here. So how do I convert that? Just remember, whatever you're interested in solving for, right? Compute the probability. What is the interval given there? That's what you want to work with, and then convert to that, and you should be good.